Dear viewers, welcome to the UGC lecture series in biophysics. Today we are going to learn the various methods to determine the protein structures. As you know, proteins are macromolecules and they contain thousands of atoms. Proteins are nothing but polypeptides. As you know, a peptide molecule is made up of amino acids. So, let us start from the basics. An amino acid is made up of an amino group and an acid group. When two amino acids are linked, the acid group of the first amino acid combines with the amino group of the second amino acid and releases a water molecule, and this has the formation of a peptide bond C double bond O high bond to NH is called C prime N. C prime N is a peptide bond. So, when we have more number of amino acids, so this way we talk about the formation of polypeptides. So, proteins are nothing but polypeptides. In our body we have more than 20,000 proteins, out of which maybe only for about 15% we know the 3-dimensional molecular structures. Each of these protein does a function. So, in case the protein does not do a function properly, which is supposed to do due to either gene modification or mutation, so many things, we have problems and they cause diseases. If you want to design drug molecules for curing any disease related to a protein, first of all you must know the 3-dimensional structure of the protein, then only you can look at the shallow region or cavity where a small drug molecule can go and bind and modulate the activity of the protein. So, 3-dimensional structure is of main importance in macromolecular crystallography. When you talk about 3-dimensional structure, this can be protein molecules or DNA molecules, protein DNA complex, protein ligand complex, protein protein complexes, etc. So, here we are going to do two parts. Let us begin part 1. The objectives will be a detailed introduction will be given to you about the various methods, of course, the limitation of earlier methods like molecular replacement method, single isomorphous replacement method and multiple isomorphous replacement method, and in the field of anomalous scattering the latest technique like single wavelength anomalous diffraction SAD and also the earlier one multi wavelength anomalous diffraction MAD, those techniques will also be described to you. The main crux of crystallography is a phase problem, which is a bottleneck, namely both in case of small molecule and macromolecular structure determination, these structures could be elucidated only when, in addition to the experimental Bragg intensities, if you know the phase angle of each Bragg refraction. So, from the known experimental intensities, if you take square root, I get a factor known as structure factor amplitude of a Bragg reflection, but unless you know the phase phi HKL of each Bragg reflection, we cannot do a Fourier synthesis of electron density to locate this electron density maxima, which is known as atomic sites. So, we have already seen how direct methods or the mathematical methods using probability theory developed by many pioneers, but particularly in a continuous way by Professor Jerome Karl and Herbert Hoffman from US. Using those, how small molecules containing up to 100 atoms could be solved for the 3-dimensional structures, for which they have been honored by a Nobel Prize in the field of chemistry in the year 1985. Even though as on today more than 11.5 lakhs small molecular structures have been determined using these methods called direct methods, these methods fail when they are applied as such to solve macromolecular structures. This is mainly due to the reason that the probability distributions become sharp only when the total number of atoms becomes small, and in case of protein molecules having thousands of atoms, we have only flat probability distribution. So, direct methods fail. Of course, by combining the technique like whatever we are going to see molecular replacement or anomalous scattering, direct methods could be used to solve macromolecular also. They have good publication in the 1982 and 83. So, that we are not going to discuss. So, to overcome the phase problem, what did people do in case of macromolecules? So, the idea conceived in the 70s was to use the coordinate of a homologous structure to solve the structure of an unknown protein. Here, what is the principle used is sequence determines structure and structure of course determines a function. So, if two structures have homologous sequences which will be revealed by their homologous structure, then we can use the known structure as a model to predict the structure of the unknown protein, which is the second molecule. So, this is the elementary idea. The molecule in the unknown unit cell is replaced by the homologous molecule whose structure is already known. So, do not ask me how it is known. Okay. Suppose you have a structure for which all the coordinates are available, three-dimensional structure is available, and now the new structure what you want to solve, you have made a crystal and you have subjected the crystal to X-ray, single crystal X-ray diffraction, we Bragg intensity, thousands of intensities, we have everything with you, but for the phases, how to go about solving a structure. This method is known as molecular replacement method or MR. But here the only drawback is that the structural homology should be at least 25% between the model structure and your structure, because your structure you know what is the sequence. Okay, we can do the homology search and homology modeling programs are there. So, at least 25%. For the situation where molecular replacement could not be applied due to the failure of this structural homology, single isomorphous replacement called SIR was proposed. So, we will see in detail one by one, but in SIR to overcome the phase ambiguity, one needs at least two derivatives, and in the second derivative the heavy atom used should not occupy the same site occupied by the first heavy atom, and this is not under the control of the experimentalist. This is a drawback. Also, as the method says iso means same, the derivatives have to be completely isomorphous, namely the cell parameters should not change even by more than 0.01%. Why we are very specific about cell parameters? When will the cell parameters change? Only when the unit cell, original unit cell is unable to accommodate the molecular size, it will expand, which means that due to the heavy atom substitution, in some cases the size may increase because of the conformational change happening because of the binding of the heavy atom. In the above type of situation, we talk about multiple isomorphous replacement method could not be used, even though we have two derivatives, and if you have the second derivative occupying the same position as the first derivative, nothing is possible. We got to go the other derivative. Even now there are many proteins lying unsolved where the other derivatives occupy the same place as the first derivatives. Then again, due to the isomorphism lost, we cannot use this technique. So, these are limitations of the MR and MIR techniques. Okay. So, if you look at the number of protein structures, three-dimensional protein structures available until 1970s, they are very less. In 80s came the advent of synchrotron radiation. Synchrotron radiation is what? A tunable source, where we get a change in wavelength even up to 4th decimal, and we will see in detail what is the advantage of this, and also the fine tuned intense beam is there. So, within few minutes we can finish off collecting the intensity data when you have synchrotron radiation, and also the resolution also become very much increased compared to the lab source. So, this is the advantage of your synchrotron. Every country has synchrotron radiation only thing. In India we have one at Indore, where you can collect protein data up to 1.5 angstrom resolution. Now, in these techniques, particularly this synchrotron based technique, data are collected either at a single wavelength, where the anomalous scattering of the heavy atom is more pronounced. This is known as single wavelength anomalous diffraction, or at 3 wavelengths, one at the peak wavelength where the anomalous scattering contributor F double prime is the maximum, and one at inflection point where the real part correction F prime is the most negative, and the third data collected either on the left or right side of the remote curves in the f double prime f prime curves. We will see later. So, first now you remember there are three methods available. One is molecular replacement, second is isomorphic replacement, which mean MIR also, then third is anomalous scattering methods. The heavy atoms are located from bifid difference Patterson and the dispersive difference Patterson respectively. About this already we have seen when we dealt about the Fourier methods. What do you mean by Patterson, what do you mean by difference Patterson, and so on. Multiple wavelength anomalous diffraction data collection is identical with multiple isomorphous replacement data collection. Here in MIR what you do? We do the chemical substitution, because instead of gold derivative you can use mercury derivative, or instead of mercury derivative you can do platinum derivative or uranium derivative, etc. But in multiple wavelength anomalous diffraction what you do is you just tune the wavelength, and each tuning of the wavelength we have the f prime parameter which will be becoming negative. So, that when it is added to the total real part f naught, we get different values for the atomic scattering factor. In other words, what I mean is, by tuning your singular wavelength to different wavelengths, I am making an atom to behave like another atom, because when atomic scattering factor changes, it is another atom. No? So, that is what this is physical changes, this is chemical changes. Since it is physical changes made with the same crystal kept in the beam, there is 100% isomorphism. So, this drawback of this isomorphism losing in MIR is overcome in MAT data. This is advantage. And initially the multiple anomalous diffraction data, as I told you, we have to have data collection at least 3 wavelengths. Now, the accuracy of these detectors used to collect data, even a difference of intensity differences between HKL reflection and minus H minus K minus L reflection, even if it is of the order of 0.5%, that could be measured. So, because of that, instead of wasting data collection at 3 wavelengths here, people have jumped to do single wavelength anomalous diffraction, where just one wavelength is sufficient, where f double prime is the largest, where we have thousands of reflections differing in intensities between I of HKL and I of H bar, K bar, L bar. So, let us now study these different methods in detail. So, let us first go to the molecular replacement method, or MR. This MR was a traditional method used in macromolecular crystallography when the structure of a related model was available. Related means a structural homology of at least 25% should be there with your unknown molecule. Why I called unknown molecule? Because I have collected data, I know the sequence, everything, but structure is unknown. Unit cell is known, but structure is unknown. That is why I call it as unknown model. For example, human phospholipase A2, which is in our body, that structure, and snake venom phospholipase A2 structure are more or less structurally homologous, but here homology is very great, greater than 95% or so. But a mere 25 to maybe 40% more homology means is better, that is all. Michael Rossman and his group from Purdue University, USA had made seminal contribution in this topic of isomorphous replacement, and you people must refer to the review for the existing literature from earlier one to 1972 compiled by Rossman, and this book is titled Molecular Replacement Method, published by Gordon and Breach, New York, USA. And at this stage I want to mention that Michael Rossman, he has received the prestigious Ewald Medal in crystallography. The first program for molecular replacement was released by Madam Paula Fitzgerald from US, and the program name was Merlot. But later, because when we use Merlot, we have to do 2 or 3 programs separately, then only we have to combine that, get the result. Now, automation came, and Professor Navaza from France, he has written a program called AMORE, Automated Molecular Replacement, and this is widely used and it is fully automatic. As I already told you when I talked about packages, there is a suite of programs called CCP4, computational collaborative project number 4, where thousands of programs related to macromolecular crystallography are deposited freely by the others and you are free to use. Then there is another program for molecular replacement called MoldRep. It is used by many macromolecular crystallographers also. This is also one of the program suite, contains the program for molecular replacement. So, now let us consider a structure of two identical units, but different orientation. Orientation one may be this, another may be that. Okay, that is all. If one does a Patterson function for this structure, we have three types of Patterson vectors that could be found. By the by, I hope you must remember what is a Patterson. Patterson just resembles a Fourier, only thing is square of the coefficient is used in a Patterson. Usually in a Fourier we use mod FH, okay, let us say modulus of structure factor. Now you have to use square of the modulus of structure factor. A Fourier gives you atomic positions, but a Patterson gives you interatomic vectors. Suppose you have n atom is a unit cell, n peaks will be there, top n peaks are Fourier peaks atomic sites, whereas in a Patterson we have to analyze n square minus n peak. So, analysis of Patterson is compulsive, but whenever you have one heavy atom dominating in a structure, that will be coming out as a prominent peak in a Patterson map. That is why people use it in macromolecular crystallography. There are two types of Patterson, we will see later. Out of these three, one is called a self Patterson vector of one unit, the set of self Patterson vectors of the other unit, because two units are there, and we talk about the interaction between two, the cross Patterson vectors formed between the two units. Raspon and Blow in the year 1962 used a rotation function, because you have different orientations are there, no, which orientation suits with your data. For example, your structure factor amplitudes for the structure we want to find. So, those are available, because you have a crystal, you have unit cell parameter, you collected data. From these intensities I can get a Patterson, and now from the homologous model also I have the Patterson. Only thing is one unit cell, this is another unit cell. Therefore, you can use that Patterson and do the orientation, rotation and translation, and whichever is giving the best, that is the best Patterson. So, that gives you a model. So, from which you get a coordinate, that is the starting picture of your unknown structure. Okay. Now, you define the rotation function in terms of three angles, theta 1, theta 2, theta 3, and we define it as in terms of Patterson p 1 of x multiplied by p 2 of y dx. Now, two self Patterson vectors will be related by a rotation, as these are in different orientations. In the cross Patterson vectors, some or all will be outside the volume extending from the origin by the overall dimensions, but the self Patterson vectors of the two units will all be within this volume. Now, when you superpose these Pattersons, they will show similar way. The superposition of the molecular self Patterson derived from different crystal forms can provide the relative orientation of the two crystals when the molecules are aligned. That is what we do, Patterson superposition. Here p 1 of x denotes the value of the Patterson at x for crystal H, and p 2 of y denotes the value of the Patterson at y for another crystal p. So, this can be homologous structure and this is the unknown structure, and this angle theta 1, theta 2 and theta 3 are the three angles which rotate the Patterson p 2 from its initial arbitrary position, and this integration or integral is over the volume u of the sphere centered on the Patterson origin. Of course, the theory of these Pattersons are complicated, but the automated program MORE is very convenient for the users. That is why most of the people they do not go into the mathematics, but since you have to learn crystallography or biophysics, we are going in depth. So, now we can have so many combinations, because three angles are combinations are many, but the best combination of theta 1, theta 2, theta 3 is the one which has the maximum for the equation we have seen, right hand side equation 1. So, this is for now we have found a best orientation. Now, that will be translated. For that we have many functions provided by many scientists. After finding the best orientation of a known molecule in an unknown unit cell, do not confuse, unknown unit cell means cell is known, cell dimensions are known, only thing is molecular structure in that cell is not known, that is why it is called unknown cell. So, now once you find the best orientation, now the absolute position has to be determined. In space group other than the tricyclic P1, the origin of the unit cell cannot be chosen arbitrarily. So, in general, for the sake of convenience, we take the origin to be on the symmetry axis. Suppose you have two symmetry axes interacting, screw axis interacting, it is convenient to keep the origin at the intersection of the screw axis and so on, because the origin selection is a big problem. So, let us see later. In these cases, whenever an exactly oriented reference molecule is translated in the unknown cell, automatically the symmetry related molecules also move accordingly and all the intermolecular vectors will change. It is only when all the molecules in the crystal cell are in the correct position, the Patterson cross vectors superpose onto those of the observed Patterson from the actual crystal structure. This is called Patterson superposition. In the Patterson superposition, it will be very noisy and with many small maxima. In the literature, many translation functions have been proposed for this purpose. Gother and Blow proposed a better translation function. The set of cross vectors of the calculated Patterson from one molecule to the second molecule can be written as P12 of u equals rho 1 of x multiplied by rho 2 of x plus u, a translation, times dx, where this rho 1 and rho 2 represent the electron densities of the two molecules. One is the homologous and the other is the molecule which you want to find. If the molecule 1 is translated, a new vector will define its origin, but at the same time molecule 2 will enter the cell, and for every value of this shift S1, a new function P12 has to be calculated. Here the intermolecular vectors are of importance, and hence translation is considered as a function of the vector t, which is the difference between S2 and S1, and this defines a local origin with respect to a symmetry element. If P observed u Patterson is the value of the observed Patterson at u, then the translation function T of t is defined as observed Patterson at u multiplied by P12 cross Patterson u comma t du. So, with the two Pattersons superposed, t will be the maximum. So, you look for the different shifts and find for whichever shift t is maximum, that is the correct one. So, this is the best translation to be applied to the best oriented molecule. So, initially we have found the best oriented molecule, it may be different orientation and we fix best orientation using cross Patterson. Now, you have to shift to the properly oriented molecule, and which is the best translation in the unit cell, that now you have found, that is all. So, now it will give you whatever homologous model you give, it will give a matrix, what is the rotation matrix to be applied to those set of coordinates and what is the translation matrix you got to apply. Once you do it, we have a new set of coordinates, and that is approximately resembling the molecular structures you want to determine. So, with that positions, since you know the positions, we can calculate the geometrical structure factor, and you can calculate the A part and B part real and imaginary components, and the phase can be calculated using tan phi equal to B part by A part. So, now you have phase. As I told you from the beginning, Fourier methods depend only on the structure factor amplitudes you get from your intensity measurement using single crystal diffraction, whether it is a crystal belonging to small molecule or macromolecule, but phases should be known. Now, since you have modeled structure properly oriented and properly translated in the unknown unit cell, now you have a model set of coordinates for the actual structure which you want to determine. Now, your intensities from which your structure factor amplitudes can be obtained are available, phases are available from the model, you can straight away go to your density calculation. This is the basic principle of your single isomorphous replacement. By measuring the intensity of Bragg refraction from native protein crystal, one knows the magnitude of the structure factors of the protein alone. That is why P means native protein, because you know intensities of Bragg refraction, we call it IP, these are mod f p square. Therefore, mod f p is nothing but square root of that I p coming from experiment. Only thing is what can the values of the phase alpha p, but this phase can take any value from 0 to pi. So, which means there is an ambiguity. So, that is what we are going to see later. Now, to overcome the ambiguity only, what you do is you do a soaking of the same protein crystal in heavy atom salt solutions containing mercury, platinum, gold, gadolinium, etc. So, what happens is in every protein more than 60% or you can say more than 50% of the regions are occupied by solvent molecule like water molecules. So, these heavy atoms will replace one of the water molecule and attach with the protein, that is known as derivative. Protein with which heavy atom H is added, this is derivative. Then you make crystal for the derivative. You can collect intensity data, take square root of this intensity data for the derivative, that is known as mod f p h. Okay. Now, how we get mod f p h? Native structure factor amplitude is there for the native protein. These heavy atoms, they have a contribution to diffraction, that is your mod f h. So, mod f p plus mod f h will be mod f p h roughly. So, now, so this is a graph showing how this alpha p, the phase of this native protein varies. It can have any value, alpha f p can be, because a circle, no, radius is same, here also mod f p, here also mod f p. Therefore, wherever you go alpha p is changing. So, there is an ambiguity of alpha p from 0 to 2 pi. Now, as I told you, once you collect intensity of the derivatives, I know is always proportional to mod f p h square. If you take square root of the intensity, I have mod f p h is nothing but mod of f p plus f h. Therefore, your f h is simply algebra mod f p h minus f p. Now, if you have this, I can do a Patterson for this. You just square it and do a map, and that will give you the positions of the heavy atom. That is the general property of Patterson. So, that is what we are doing. But here, if you look at the solution of this equation, that can be obtained by using a derivation. The final formula is cos of alpha prime, something is coming. Now, this is known, everything is known. Therefore, you can find cos of alpha prime, but cos of theta is same as cos of minus theta. So, now when you determine an angle alpha prime from cosine, this equation is true whether the alpha prime is positive or negative. So, we have ambiguity. So, now if you look at the total value for the phase of the protein, it will be either heavy atom phase plus alpha prime plus or minus pi by 2 or heavy atom minus alpha prime plus or minus pi by 2. So, this twofold ambiguity is there, but there is a technique known as quasi anomalous scattering. They say that whichever phase is closer to heavy atom phase, that is the true phase of the your protein. So, now we have the theory for SIR given by Michael Rassmann and also by Professor Karta and Parthasarathy. I want to mention that Karta is a postdoc of Professor G. N. Ramachandran and Parthasarathy is a doctoral student of Professor G. N. Ramachandran, and Parthasarathy did his second PhD in the US, Buffalo, with Harker, an eminent scientist in the field of background molecular crystallography. For the MIR technique, we use Harker section. It is a fantastic contribution given by Harker and Karta and Parthasarathy. So, now let us stop with this and we will continue the rest. Climax is there, you got to know the diagrams clearly. So, let us stop with this, we will continue in the second part. So, thank you for listening.